kind of pessimistic, I guess. I've got this policy in place for quarantine isolation exams. So if any of you get called in, like hopefully if you're here, you're feeling good, and I hope that continues. But if you get called in for isolation based on contact tracing, there is a mechanism by which you can take the exam on Friday if you want. I also extend an offer of an excused absence if that happens. So just be, now that we're getting down kind of close, certainly like if Wednesday night they call you, I don't know how it works actually. We have like security that comes and gets you or something. Yeah, is that what we do?
They call you and then the van comes and picks you up.
That reminds me there's an election next week, you should vote. Anyway, yeah. So anyhow, yeah, if something happens Wednesday night, Thursday morning, just be in touch with me as quick as you can. And like I said, no questions asked, you go to quarantine or isolation, you can take an excused absence. If you do that, anyone with an excused absence, you're basically like, if exam 2 is excused, exam 1 and 3, the average of that score goes in place of exam 2. And that's it, we're at capacity, all right. Cool, all right, so let's see, let's do what was that? No, okay. All right, predict a product over there. And then over here, so work either one of those that you like. You can ask me some questions if you want. Yeah.
I'm sorry. For the one on the left, I can't read what it says on the top. Up under excess, what molecule is that?
Yeah, it makes it hard if you can't read. I mean, not if you can't read. Not if you can't read my writing. It is hard if you can't read, but it's. I'll try to write it larger. Can you read that?
Yes, sir.
Okay. trouble with this, I'll give you a hint. There's more than that, that's not all of it, that's just some. So that stopped a lot of writing, so either you all have that product, or simply showing you NMR data has frozen you in your tracks. You can, people got answers on the second one? A little more straightforward, okay. I'll give you a few more minutes on the first one. Yep,
Next to the 3.6, that's a T.
that is a T, yeah.
Okay.
Singlet at 3.2, triplet at 3.6.
Okay.
All right, so I'm going to give you a little. Let's talk about the rate equation first. So, you guys have quite a bit of experience with, or not quite a bit. There are quite a few Wiley Plus problems on this, the worksheet, and I would say about that substitution elimination. There's a key on there. That and the second I'm going to try my best to look at everybody's substitution worksheet. The spectroscopy I'm probably not going to get to. I'm not going to be able to grade everybody's, so you should consult the key and bring questions to me. I'll try to make comments. I'd especially like to comment on everybody's mechanism, because this, I haven't, like, you didn't have to draw a mechanism on the first exam. You'll almost certainly have to draw a mechanism on this exam. So I'd like, if you're doing something really, come back to a professional. I was about to use an unprofessional adjective. If you do something really crazy, like, I would like to be able to stop you, or at least try to correct you. But I'm not, like, actually assigning points is going to be out the window. But you should look at the key. Like, I basically am going through it alphabetically, so if, especially if you're at the end of the alphabet, maybe go and take a look at the key right after class. So which one of these do you think is first, fastest? Sorry. Why do you think let's do this first. Really, to answer this question, you've got to figure out the mechanism. All right. So, do you have a strong nucleophile or base?
No.
people saying yes, got some people saying no. Those of you who think yes, why do you think what is the strong, is ethanol a strong base? Anybody think ethanol is strong base? So why, I saw some people, I'm not trying to call any names, but I saw some people saying, yeah, there's a strong base. So what is the strong base, if that's, anybody brave enough to tell me? No? Thought if I couched it that way, like brave, you could claim a noble trait. So yeah, there's no strong base or good nucleophile. All right, so we've got elimination reactions. It's either going to be E1 or E2. In order for it to be E2, there has to be a strong base. And what I was trying to draw out, and I don't know if this is true or not, there's either two ways that you think there's a strong base here. One is you just think ethanol is a strong base. All right, this one doesn't work nearly as well, and I shouldn't be advocating, I'm not advocating drink. Ethanol is poison. All right, so all of you who enjoy the drink, you're drinking poison. It can be enjoyable, but it's still poison. All right, so water works a lot better. You can drink water. We all drink water. It's, you know, it doesn't burn your mouth, smooth going down. That doesn't work quite as well with ethanol, right? If you drink straight ethanol, your throat is going to burn. But it's not actually from an acid-base reaction. It's just from a desiccative kind of reaction. The ethanol will dry that out. So ethanol itself, if you pour it on you, it's not going to dissolve your skin or anything like that. Okay, sodium hydroxide, if you took concentrated sodium hydroxide solution and poured it out on your skin, it would actually dissolve your skin. All right, strong base is really dangerous. Ethanol's, it's going to sting a little, but again, that's just kind of an evaporative chemical thing, like when you get, vinegar in a hangnail or something. So ethanol itself is not a strong base. Sometimes people look at this and they see the OH, right? And if this was NaOH, that would be a strong base. Okay? And so you see that OH and you're thinking, oh, I got hydroxide in there. This OH is not a hydroxide, right? That OH is covalently attached. So the oxygen has two bonds, it's neutral. It's a weak base because it's got electrons, but it's not hydroxide. In order for that to be hydroxide, the carbon-oxygen bond would have to break. You'd get a primary carbocation and hydroxide, and that's not going to happen. All right, so there is no strong base here, and that means this elimination has to be an E1 elimination. Okay, fair enough. What's the slow step in an E1 elimination? The leaving group leaving is the slow step in an E1 elimination. So the slow step is going to be the leaving group leaving to give a carbocation. Okay, so do you guys want to stick with your answer that the secondary is fastest? Good. All right, so if you thought the secondary was fastest, did you think it was an E2? All right. And actually, sounds very pretentious. There's not much difference, so there would be a huge difference in SN2 rate between a secondary halide and a tertiary. All right, the tertiary is not going to react. Secondary is going to react. But in an E2, that's really not the case. All right, if it's being driven by the base, both of them are probably going to react at about the same rate. It would be really hard to tell which one's faster. In the E1, though, that's the rate determining step, is that mechanism right there, the leaving group leaving. So now what do you think is number one? Iodide, second one. So this is going to be 1, and the reason is, why is that one faster? So if you're comparing, actually the top 3, so the iodide and chloride, right? Iodide's a better leaving group than chloride. Both give the same carbocation, the same tertiary carbocation. So really, you can only ever compare 2, right? I can compare this one and that one. and then I can compare that one and this one. So I know that the chloride, by figuring out that the second one is faster than the third one, I've set up the second one being number 1. But that doesn't necessarily nail down that this one's number 2. So compare that to the bottom one and the top one. What's number 4, I guess I should ask. That's good. That one, number 4 is hard. So what's number 2?
Chloride.
Right. So here you're going to get to a tertiary chloride. The only difference between 2 and 3, the second and third one here, is the leaving group. So really, ideally, when you run a scientific experiment, you want to change one variable. Right? Everybody says that. That's actually really hard to do in practice. It's easier in chemistry than it is in biology. Physics, it's usually easier. So in biology, a living system, I mean, even if it's not alive, if you're just dealing with a cell, say, or an accumulation of biomaterial, there's a lot of difference. And certainly in any living organism, you can't control, like if you do a drug trial, and I'm going to give a drug to 1,000 people and see what the effect is, you're not exactly replicating the same experiment 1,000 times, right? Because we're all chemically different. There's a lot of similarity between human to human, but we're not exactly the same. Okay, so that's why really for any kind of medical trial, you need enormous numbers to really draw conclusions, which is expensive and can even be dangerous. And so we tend to make a lot of educated guesses, especially early on in medical studies. In chemistry, it's a lot easier. Right? I can do this reaction exactly. I can take the ethanol from the same place. I can put it all in the same 100-degree bath. And then all I'm doing is changing the molecule I add. So 2 and 3, I'm changing the leaving group. That's all I'm doing. I get the same carbocation. All that changes is the leaving group. So you guys said this one is 2. Now, so that means you've decided the bottom one and the top one are 3 and 4 in some order. And now you've got 2 changes, right? The leaving group changes, and the cation you get changes. So that's a harder one to come up with. So who thinks the bottom one is slower? Who thinks the top one is slower? Pretty good turnout. Yeah, so the top one is slower. It would give a better cation, but hydroxide is not a leaving group. Okay, so essentially the rate, this is like a tertiary halide in an SN2 reaction. Doesn't matter how good the leaving group is, tertiary halides can't do SN2. So that's 0. 0 is as slow as you can go. So this top one would be 4, and that leaves the bottom one to be 3. So a secondary chloride is going to do SN1 faster than a tertiary alcohol. Unless you to get the top one to react, so now if we did this, if the conditions were different, right, if we used acid there, if we put acid into that reaction, we would protonate the OH, then we'd have water be a leaving group, and that would actually be a really good reaction. Okay, but that's not the conditions that we're running here. All right, good. So again, when you look at a problem like this, try to identify the single change. And then I try to design them so, like if you find the fastest one, then you find the second fastest, there's going to be kind of a slow change along there, yeah.
If you were doing an SN2, would you go with the one that was the least sterically hindered?
Yeah, so actually, if this was SN2, it would be a tie. Let's do SN2. So this is E1, and the SN2 rate only that secondary chloride can do the SN2 here. So tertiary alcohol, you don't have a leaving group, and it's tertiary. Like that would be a good solvent maybe for an SN2 reaction. The second and third ones, if you put in anything that's reasonably basic, so like any SN2 nucleophile is probably going to be basic enough to do an E2 on those. There was another problem in the problem set where you had a tertiary halide. You basically had what would be SN2 or E2 conditions, like that, and then you use the temperature to conclude it would be SN2. But it was a tertiary halide, so it can't do SN2. You know, if you decide it's SN2 or E2, and the carbon with the leaving group can't do SN2, then it's got to be E2. Okay. Anybody want another minute on the reaction? All right, look, everybody has written down a product, right? All right, so go ahead now and draw a mechanism for this reaction. You at home, I'm going to hit pause, and you can do this later. Not later, you can